Let's talk about tangents to polar curves. To find a tangent line to a polar curve r equal to f of theta, we regard theta as a parameter and we write its parametric equations as x equal to r cosine of theta, which is going to be the same thing as f of theta times cosine of theta. And we're going to write y as y equal to r sine theta, which is going to be f of theta times sine theta. So this x equal to r cosine theta, that came from our conversion from Cartesian to polar coordinates. And same thing with y equal to r sine theta. That also came from our conversion of Cartesian to polar. When we look at the result over here, you see we have two functions of theta multiplied together for both the x-coordinate and the y-coordinate. So what we want to do is we want to use the methods of 10.2 to find the slope dy dx, right? Dy dx this is the slope of the tangent line. So how are we going to do that? Well, dy dx, as we saw earlier, is going to be equal to dy d theta, because theta is our parameter this time, divided by dx d theta. When we take the derivative of dy d theta, we're going to need to use the product rule. Your first function is f of theta, and your second function is sine of theta. So when we use the product rule, that dy d theta is going to be f prime of theta, the derivative of the first function. You keep the second, which is sine theta, plus take the derivative of the second thing, which is cosine of theta, and then you keep the first thing, which is your f of theta. That's the numerator. To find the denominator, we are going to take the derivative of the first function, f of theta, which is going to be f prime of theta. You keep the second thing, which is the cosine of theta. Plus, when you take the derivative of the second thing, you're going to get negative sine theta. So let me change that plus to a minus. It's going to be negative sine theta times the first thing, which was f of theta. Okay, so we can express this in terms of r, because remember our function f of theta was really what we were calling r. So let me write this formula in terms of r. So this is going to be dr d theta times sine of theta plus r cosine of theta divided by dr d theta times cosine of theta minus r sine theta. So this is the formula we get for dy dx. I'm going to highlight this formula over here. It's something you either want to be able to derive or you want to memorize it, but that's important for us to find the derivative of polar curves. So just to reiterate, this is the slope of the tangent line. Okay, so why don't we take a look at example 12. We'll just do the derivative part and we'll find the rest of it in class together. So in this question, we want to find the slope of the tangent line to the curve r equal to 1 plus sine theta. So this is a cardioid because the 1 and the 1 here, the implied one here, are the same. And we want to find the slope when theta is equal to pi over 6. So we'll do that on this video. And then in class we'll find all the points on the cardio where the tangent line is horizontal or vertical. All right. So why don't we write down what our x and what our y are going to be first. So our x is equal to r cosine of theta, and that's going to be 1 plus sine theta times cosine of theta. And we could simplify that to be cosine of theta plus sine theta cosine of theta, like that. If we write down what y is going to be equal to r sine theta, and that's going to be 1 plus sine theta times sine of theta. And we can see that this is going to equal to sine theta plus sine squared theta. Okay, so we know that when we want to calculate our derivative, dy dx, we had our formula from before. That's going to be dr d theta sine theta plus r cosine theta all over dr d theta cosine theta minus r sine theta. So let's try to calculate what this is. Now my r is 1 plus sine theta, so our dr d theta, maybe I'll calculate that off to the side just because we need to use it. Dr d theta is going to be equal to, the derivative of 1 is 0, and the derivative of sine is cosine, so that's cosine of theta. Okay, so we're going to use that in calculating this. So dr d theta would be cosine of theta. The sine theta stays there, and then we have plus the r cosine theta is just the x thing, so that's going to be cosine theta plus sine theta times cosine theta. So this part is just the same thing as this part, so I just copied this and put that right here. Okay, cool. So what about the denominator? Let me put the line there. Our dr d theta we just said was cosine of theta, and then we have cosine theta minus the r sine theta right here. That's really the same as y. So we're going to write this, but we should make sure that we put that in parentheses because there's a negative here. So let's put parentheses sine theta plus sine squared theta, like that. Okay. So I'm tempted to end this here, but I see that we could do some simplification. So I think maybe we should simplify this a little bit. So let's do that. So let me put the line here. Okay. The first thing I kind of want to point out to you is, let me use the highlighter. We have this cosine theta, sine theta, and this sine theta, cosine theta. So we can use the double angle formula. Sine of 2 theta is equal to 2 sine theta cosine theta. Right, the two parts that are highlighted in red are, when I add those two red parts together, I get 2 sine theta cosine theta. So I can really write this as cosine of theta plus sine of 2 theta, like that. And I can distribute the denominator. So when I distribute the denominator, I'm going to get cosine squared theta minus sine theta minus sine squared theta. So now I could use another double angle formula, this time for cosine. Cosine 2 theta is equal to cosine squared theta minus sine squared theta. So really, in the end, my derivative can be written as cosine theta plus sine 2 theta divided by really cosine 2 theta minus sine theta. So this is our simplified derivative, and I will highlight that for you here. Okay, so we'll do the second half of example 12 in class together. Take care, everyone.